So this will be an intro into chapter 10 to just check whether linear correlation is appropriate for data. So a lot of this is review, starting with the idea that if we have an R value between -1 and +1, we've seen that before. It's been a while, but we graphed scatter plots and we said an R closer to 1 or -1 is stronger, okay? That does change kind of depending on the sample size, but that's once again not as much of an A basket issue to me. It is important though that R is not enough to tell me whether something's linear. And so if I look at these 4 pictures, what I love about these pictures is that all 4 of these actually have the same R value. And all of them are relatively strong. So all of these, I think they had an R value of like, right here, 0.816. Okay, so here's a nice little scatter plot along the line. Here's the same line, but it has this little curve along it. That pattern is bad. That tells me that even though it has a strong R value, a linear correlation is not appropriate. We should not see a pattern. There should be no pattern. Curves are bad. Okay? The second one on the bottom left, it's not too bad. Most of them are following along a point, but then we have this one point right here that affects the R quite a bit. That creates an outlier. So if there's an outlier, like if there's, if we have, what is this, 10, 11 points, and I have one of them just way off, then we don't just ignore that. Then maybe a linear pattern isn't appropriate, okay? And the second, if there's basically a cluster of points with a point out here, that once again, that outlier, this is not very good. Out of the 3, the top left is your better graph, okay? I want the data to fall randomly around the line. It's okay if the points follow more of a straight line, but you can't have any outliers like that. Okay? What I want you to be able to do is you should be able to check whether something's linear, but we shouldn't start by looking at the graph. We should start by looking at the R value. And so that's where I say down here that when I'm going to check for linearity, first thing I'm going to do is I'm going to look at the R value. Is it strong? Because if I have an R value that's close to 0, if it's 0.1, then I don't really care what the picture looks like because that's going to be a horrible predicting line. It won't fit the data well. So I want a strong R value first and foremost. So what does that mean? Close to 1, close to -1. The second thing I would do is I would look at the actual graph and say, is there any patterns? If there's a pattern, then no, a linear model is not appropriate. Okay? Are there any outliers, any points that are way off? If there are, then no, this linear model is not going to be appropriate for at least that point. So the other thing that we can do is we can actually run a test on R. Okay, R is the linear correlation for the sample data. If I want to do the correlation for the actual correlation of the population, that's this kind of P. It's called pho. And we round this to 3 digits and has no units of measure, but we can run a test on pho. We can run a test on whether there is a correlation, whether there's a strong correlation or not. I will not have you do that on the test, but I do have some of that on maybe 1 or 2 questions on the homework, just so you can see how to do it. If you do it on the test, it's not wrong. If you want to do that to check linearity, it's not wrong, but you still are going to need some other sketches anyway. So how we do it is we set up this test, and the null hypothesis is that pho equals 0. When I say pho equals 0, that means that there is no correlation. This implies it is weak. Okay? So if we fail to reject 0, that supports there is no correlation. That means there is a super weak relationship. We should not use linear regression. Okay? If we reject 0 and we conclude not 0, that supports linear correlation. That means, well, R is not 0, so there is some correlation here. Okay? So these are the phrases that I use. If the p-value is greater than alpha, we fail to reject that pho equals 0, supports that there is no correlation. Or if the p-value is less than, we reject 0 and conclude it's not 0, which supports linear correlation. How could we run this test? Well, we could run the test in the calculator, actually. Right here is going to be your instructions. So if you're doing it on the homework, these are your instructions on running the test. Once again, don't have to do this on the quiz or the test, but it is an option. Okay? So take a minute let's go ahead and type this data into our A and our B. So X is the weight, Y is the miles per gallon, and would we expect there to be a correlation between the weight of your vehicle and its miles per gallon? Yeah, that makes sense that we would have some correlation between those two, right? So if we type in that data, and I've gone and typed in the data here already, you need to make sure that you name it. So I just call the first one X is convenient, and the second one is Y. If you're going to keep doing this with questions, you want to make sure that you create a new document if you want to keep using X and Y, or you could use a less generic name, and you could have called this weight and miles per gallon or whatever it is, but you can go ahead and make sure that's it. Oh, I typed in the wrong data, so let me fix that real quick. See what happened is I'm actually in an old document with old data when I named X and Y. So what you want to do is you want to make sure that you have a new document if you want to use the names again. No, I don't need to save that. And then in there we type in the new list in here. I already have the list, I think, saved, so I should be able to paste it and see. There's our data, okay? And now I can call it X and Y because I'm in a new document. All right, so how do I run the test again? Menu, statistics. This is a test, and it is called a linear regression t-test. Click there. My X list was in A, and then put the brackets. My Y list was in B, and our alternative is not equal to. You can actually do greater or less than. We just do not equal to for testing linearity. And the results need to go in C, so just at least pass the data. So what do we have from this? Well, we have a t-value of negative 6.39. So our null alternative hypothesis, a t of negative 6.39. We have a p-value of 0.0014. We have a degrees of freedom, which should be, I think, the number of points minus 1. So maybe not. Looks like it's 5. Maybe there was 6 data points. 5. And then we have an equation that they give us. So they give us the what is called the least squares regression line. They give me the A and the B so that I can fill in this equation and go y is equal to 54.695 plus negative 0.0079x. That's the A and B in this equation. So 54.695 plus negative 0.008, and I don't know why I can't see it in there, but there's a little x in there, okay? It gives us other useful things. It gives me the r and the r squared. So if I scroll down, it gives me the r, negative 0.94. It gives me the r squared, 0.89. Both of those tell me kind of a relative strength of the equation. The fact that our r is so close to 1, really closer to negative 1, implies this is a very strong linear relationship. But I can actually, like I said, run a test on this, and we have, I didn't specify an alpha, I don't think. Let me go back and check. So no, so we'll use an alpha of 0.05. And we would say, since that p-value is less than alpha, we reject the null hypothesis that p equals 0 and conclude p does not equal 0. What does that really mean? We are concluding that there is a linear relationship here. Okay, that is my least favorite way of actually testing, but you can do it that way. What I would want you to do is this, and we've already started talking about this. First, look at the r. If it's close to 1 or negative 1, call it strong. Second, look at the graph. Okay. Third, look at the residual plot. You're like, what the heck's a residual plot? We'll talk about that right now. Okay. So second, if I look at the graph, and I've already done a sketch here, but we'll do it on the calculator as well. I go from the home screen. Our fifth box over is going to be our data and statistics. Clicking on the X, we add X. Clicking on the Y, we add Y. If I look at this, does this appear to have a roughly linear relationship? Like, I don't know, it just looks like a bunch of dots, okay? Well, you can add, under Analyze, I can add the regression line a plus bx. This is going to be useful to do anyway. So once you graph it, go to Analyze, Regression, a plus bx. Notice right here, that's the same formula we got from running the test. So we can get the formula this way as well. But notice how most of those points are falling kind of normally, kind of randomly along this line. There's no pattern, but they're falling along this line. Okay, that's a good argument for linearity. Our third option is to do what's called a residual plot, and that would be Menu, Analyze, Residuals. This used to actually be grayed out, but when you add the regression line, it creates residuals. And I go down here to show residual plot, and what this does is it shows me how far the points fall up and down below this line. And we want no pattern in the residual plot. Okay, there shouldn't be any curvature, there shouldn't be any bell, there shouldn't be any pattern around this line. I don't know where the next point's going to fall. These are randomly falling above and below. This is a good argument for linearity. Okay, if you want to run the test, you can. But ultimately, if you can do this on your calculator, then all I need you to do is first look at R and R squared. Is it strong? If it is, that's a good argument. Second, look at the graph. Does the graph seem to fall along that line? And third, do a sketch of the residual plot to see what it looks like. We want there to be no pattern on the residual. Okay, so that's going to be kind of the intro of checking linearity. You have a couple options to do that, but it should be a pretty easy assignment, and we're going to build on that in the upcoming section.